Hello again, this is Michael Levitt. This is part two of my series of short talks. This one is about curve fitting. Again, Michael Levitt from Stanford Medical School, and this is curve fitting as it relates to epidemics. So we're going to start out with certain functions, mathematical functions, that describe growth. One well-known function is the sigmoid function. It basically looks like this. It starts out low, grows, at some point starts to slow down, and ends. The sigmoid function is defined mathematically like this, or else like this. This is not too complicated, I guess, if you know at least college math, and it's easily coded in simple programs like Excel or MATLAB. Now, this is showing this growth on this linear scale, i.e., we're going up from 0 to 20,000 and so on. What does the growth look like on a log scale, which will emphasize what's going on over here? So now we have our log scale going from 1, 10, 100, and so on. Now we're going to show the growth again. And now it's basically just like we had for our limited exponential growth in our previous talk. It grows exponentially and then stops. And here we have a real mathematical function that seems to behave just like a limited exponential growth function. We have the total number of cases. We also have the slope. And as you will guess by now, the slope is fixed. For the exponential part, or the gradient is fixed, it then slows down and goes to 0. As we see this happens, now it's happening in a very nice, smooth mathematical way. And then finally, the number of cases is shown here, and this just increases, gets to a maximum, and comes down again symmetrically. As I said, this is a very symmetrical function, and the symmetry, if outbreaks were like this, would be interesting, because when you get to the maximum, it means you've gone through half the number of cases that you're going to get, or death, depending on what you're looking at. So when you get to the maximum, you can predict that the total number of cases will in fact be double the number on this day. That is actually simple-minded, and we'll see why. Now let's look at a different growth function. This one has a strange name, not sigmoid, but Gompertz growth function. It has a very interesting pedigree. It was actually published by a man called Gompertz in 1825 in the Proceedings of the Royal Society. Its mathematical form is slightly more complicated than we had for the sigmoid function, and in some ways, it sort of looks the same. Here we start out, function is flat, increases, and then slows down. It sort of looks the same, but if we look at this function in more detail and use a log scale, we see that in fact, it's quite different. On a log scale, it comes shooting out of the baseline, doesn't ever seem to be straight, and then levels off. What about its growth? So this function, I said it, maybe it is straight. Remember, any straight line, any part of a curve, if you look at it, can look like a straight line. So you really have to look at the slope of this mathematically, and the slope of this line is, surprise, surprise, a straight line. In other words, on a log scale, the slope of this curve starts out very high and is decreasing all the time linearly. This means that the Gompertz function actually wants to slow down. This could be described as, say, a bullet coming out of the muzzle of a gun. It's going fastest when it leaves the gun, and then it progressively slows down because of air resistance. Finally, the number of cases for the Gompertz function looks rather like we had for the sigmoid function, but now you see that there are probably twice as many cases after the maximum as there were before the maximum. So these functions are quite similar, at least on a linear scale. Let's just compare them. Here we have the two functions on a linear scale going up linearly in steps of 20,000. This is the sigmoid function, nice and symmetric. This is the Gompertz function. It looks like it's been delayed, and it looks like you pushed it back 3 days and would superimpose. These functions have been set up so that their maxima, where the maximum number of cases are, is exactly on the same day. So this is actually correctly set up. Okay. Let's look at the comparing the growth functions of these two situations on a log scale. Again, 1 to 1,000, 100 to a million. This is the familiar sigmoid function, starts growing exponentially. This is the Gompertz function, starts off very curved. And finally, let's just look at the functions again. Sigmoid function, we have this peak, this decreasing gradient or slope or growth value starting out here. For the Gompertz function, it comes shooting out and then that slows down of its own will. This is the important thing to see here, and the number of cases is asymmetric. The final thing I just want to emphasize is look at the growth functions, because this is where these two functions really differ. For the sigmoid function, we have exponential growth, which then stops as if it hits a wall. For the Gompertz function, the growth from the very, very first case is slowing down. So these two functions are different. Some quick conclusions. Different growth functions have different properties. Both of these growth functions are described by exactly the same three parameters. Some growth functions grow exponentially, others do not. And this may have implications for the growth and control of epidemics. Thank you so much. We're off now to the third part.